To measure the resistance to ground of a grounding electrode according to National Electrical Code 250.56, firstly, disconnect all other grounding conductors. Remove any grounding conductors connected to the electrode, for example, electrical system, plumbing, and so forth. Secondly, establish a temporary ground reference. Drive a ground rod at least 6 feet away from the grounding electrode you want to test. This will serve as the ground reference point. Thirdly, connect a ground resistance tester. Connect the tester's terminals as follows. The black, live terminal goes to the grounding electrode under test. The red, neutral terminal goes to the temporary ground reference. The green, ground terminal is not connected. Fourthly, take multiple measurements. Measure resistance at the following points. At the base of the grounding electrode, at intervals of 6 feet along the length of the electrode, if applicable, and at a point halfway between the electrode and the temporary ground reference. Fifthly, average the measurements. The average of the resistance measurement should be less than 25 ohms. Resistance to ground can vary due to several factors. Soil type is a significant factor. Dry, sandy soil has higher resistance than moist clay soil. The point of measure also affects resistance. Resistance decreases closer to the electrode. Moisture is another factor. Wet soil has lower resistance than dry soil. Soil conductivity also plays a role. Soil with high mineral content has lower resistance. If the average resistance is less than 25 ohms, the grounding electrode is considered effective for a 60 amp service. If the average resistance is greater than 25 ohms, you may need to install multiple grounding electrodes and connect them together. Treat the soil around the electrode with a conductive compound, or consider using an alternate grounding method, such as a ground rod or buried conductor. The grounding electrode system is a critical safety component of any electrical installation. Its primary function is to provide a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. This ensures that dangerous voltages are quickly removed from conductive surfaces, minimizing the risk of electrical shock. The National Electrical Code, or NEC, provides detailed requirements for grounding electrode systems to ensure their effectiveness and safety. Section 250 of the NEC covers the general requirements for grounding and bonding, including the types of grounding electrodes permitted, the methods for installing them, and the requirements for connecting them to the electrical system. One of the most common types of grounding electrodes is the ground rod, which is typically made of copper or copper-clad steel and driven into the ground. The NEC specifies minimum requirements for the size and length of ground rods, as well as the depth to which they must be driven. In addition to ground rods, other types of grounding electrodes are permitted by the NEC, including ground plates, underground metallic water pipes, and concrete encased electrodes, also known as UFA grounds. Each type of grounding electrode has its own specific installation requirements, which must be followed to ensure compliance with the NEC. The connection between the grounding electrode and the electrical system is made using a grounding electrode conductor, which must be sized according to the requirements of the NEC. The grounding electrode conductor connects the grounding electrode to the main grounding busbar in the electrical panel, which is then connected to the neutral conductor of the electrical system. Proper installation and maintenance of the grounding electrode system are essential for ensuring the safety and reliability of the electrical installation. Regular inspection should be performed to check for corrosion or damage to the grounding electrodes and conductors, and any necessary repairs should be made promptly. In addition to the grounding electrode system, bonding is another important aspect of electrical safety. Bonding refers to the practice of connecting all metal parts of the electrical system together to create a low impedance path for fault current. This includes metal conduits, metal enclosures, and metal equipment housings. By bonding these metal parts together, the risk of electrical shock is minimized, as any fault current will quickly flow back to the source, causing the overcurrent protective device to trip. The NEC provides detailed requirements for bonding, including the types of bonding conductors permitted, the methods for installing them, and the requirements for connecting them to the electrical system. Proper bonding is essential for ensuring the safety of electrical installations, and it should be performed in accordance with the requirements of the NEC. Understanding the principles of grounding and bonding is essential for anyone working with electrical systems. By following the requirements of the NEC and taking the necessary precautions, the risk of electrical shock can be minimized and the safety and reliability of electrical installations can be ensured. Soil resistivity is a measure of how much the soil resists the flow of electrical current. It's a critical factor in designing effective grounding systems, as it directly impacts the performance of grounding electrodes. Soil resistivity is influenced by several factors, including soil composition, moisture content, temperature, and the presence of dissolved salts. Different soil types have different resistivities. For example, clay soils generally have lower resistivity than sandy soils due to their higher moisture content and greater concentration of conductive minerals. Moisture content plays a significant role in soil resistivity. As the moisture content of the soil increases, the resistivity decreases. This is because water is a good conductor of electricity, and it helps to facilitate the flow of current through the soil. Temperature also affects soil resistivity. As the temperature of the soil increases, the resistivity decreases. This is because the mobility of ions in the soil increases with temperature, making it easier for current to flow. Dissolved salts can also lower soil resistivity. Salts like sodium chloride and calcium chloride are good conductors of electricity, and they can significantly reduce the resistivity of the soil when they are present in high concentrations. Measuring soil resistivity is an important step in designing an effective grounding system. There are several methods for measuring soil resistivity, including the 4-point method, the Wenner method, and the Schlumberger method. The 4-point method is the most commonly used method for measuring soil resistivity. It involves driving 4 electrodes into the ground in a straight line and measuring the voltage drop between the inner 2 electrodes when a current is passed between the outer 2 electrodes. The Wenner method is similar to the 4-point method, but it uses a different electrode spacing configuration. The Schlumberger method is a more advanced method that is used for measuring soil resistivity at different depths. Once the soil resistivity has been measured, it can be used to calculate the resistance of a grounding electrode. The resistance of a grounding electrode is the opposition that the electrode presents to the flow of current into the earth. The lower the resistance of the grounding electrode, the more effective it will be at dissipating fault current and protecting people and equipment from electrical shock. There are several factors that affect the resistance of a grounding electrode, including the size and shape of the electrode, the depth to which it is buried, and the soil resistivity. The larger the size and the deeper the grounding electrode is buried, the lower its resistance will be. The lower the soil resistivity, the lower the resistance of the grounding electrode will be. In areas with high soil resistivity, it may be necessary to install multiple grounding electrodes in parallel to achieve the desired level of grounding performance. It is also possible to reduce soil resistivity by treating the soil with chemicals or by adding conductive materials to the soil. Grounding is not just about protecting people from electrical shock. It also plays a critical role in protecting sensitive electronic equipment from damage due to power surges and other electrical disturbances. A well-designed grounding system can help to reduce noise and interference in electronic circuits, improving the performance and reliability of electronic equipment. Grounding is a complex topic, but it is essential for ensuring the safety and reliability of electrical systems. By understanding the principles of grounding and the factors that affect grounding performance, it is possible to design and install effective grounding systems that will protect people and equipment from electrical hazards. The grounding electrode conductor, often referred to as the GC, is a vital component in any electrical system, serving as the critical link between the system's grounded conductor, typically the neutral, and the grounding electrode. Its primary function is to provide a low-impedance path for fault currents to flow back to the source, facilitating the rapid operation of overcurrent protective devices such as circuit breakers or fuses. This swift response is crucial in preventing electrical shock hazards and minimizing damage to equipment. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as outlined in the National Electrical Code, specifically Table 250.66. This table provides a straightforward reference for selecting the appropriate GEC size based on the size of the largest ungrounded conductor or equivalent area for parallel conductors. The NEC mandates that the GEC be made of copper, aluminum, or copper-clad aluminum. Copper is the most commonly used material due to its excellent conductivity and corrosion resistance. Aluminum is a less expensive option, but it requires a larger conductor size to achieve the same level of conductivity as copper. The GEC must be securely connected to both the grounded conductor and the grounding electrode using approved methods such as exothermic welding, listed pressure connectors, or listed clamps. These connections must be mechanically strong and electrically conductive to ensure a reliable and long-lasting connection. The NEC permits the GEC to be run either exposed or concealed. If run exposed, it must be securely fastened to the surface on which it is installed and protected from physical damage. If run concealed, it must be installed in a raceway such as conduit or electrical metallic tubing. In some cases, the grounding electrode conductor may need to be protected from physical damage by enclosing it in a rigid metal conduit or other approved means. This is particularly important in areas where the conductor is exposed to vehicular traffic or other potential sources of damage. The grounding electrode conductor must be continuous, meaning that it cannot be spliced or jointed. This ensures that there is a continuous, low impedance path for fault currents to flow back to the source. In situations where multiple grounding electrodes are used, each electrode must be connected to the GEC using a separate conductor. These conductors must be sized in accordance with the NEC and connected to a common termination point. Regular inspection and maintenance of the grounding electrode conductor are essential to ensure its continued effectiveness. The conductor should be checked for signs of corrosion, damage, or loose connections. Any necessary repair should be made promptly to maintain the integrity of the grounding system. The grounding electrode conductor plays a critical role in protecting people and equipment from electrical hazards. By providing a low impedance path for fault currents to flow back to the source, it helps to ensure the rapid operation of overcurrent protective devices, preventing electrical shock and minimizing damage to equipment. Proper installation and maintenance of the GEC are essential for ensuring the safety and reliability of electrical systems. Bonding jumpers are an essential component of electrical safety, playing a critical role in creating a low impedance path for fault current to flow back to the source. Their primary function is to connect metallic parts of an electrical system together, ensuring that all conductive surfaces are at the same electrical potential. This minimizes the risk of electrical shock by providing a safe path for fault current to flow, allowing overcurrent protection devices to quickly trip and energize the circuit. Bonding jumpers are used in a variety of applications, including connecting metal conduits, metal enclosures, equipment grounding conductors, and other metallic parts of an electrical system. They are typically made of copper or aluminum and are sized according to the requirements of the National Electrical Code, specifically Table 250.102. The size of the bonding jumper is determined by the size of the circuit conductors that it is intended to protect. The NEC provides specific requirements for the installation of bonding jumpers. They must be securely connected to the metallic parts that they are intended to bond using approved methods such as exothermic welding, listed pressure connectors, or listed clamps. These connections must be mechanically strong and electrically conductive to ensure a reliable and long-lasting connection. Bonding jumpers must be protected from physical damage. This can be achieved by enclosing them in a raceway such as conduit or electrical metallic tubing, or by securely fastening them to the surface on which they are installed. In some cases, bonding jumpers may need to be protected from corrosion. This can be achieved by using corrosion-resistant materials such as copper or stainless steel, or by applying a corrosion protective coating to the bonding jumper. The NEC requires that bonding jumpers be identified with a green color or with a green color and one or more yellow stripes. This makes it easy to identify bonding jumpers and ensures that they are not mistaken for other types of conductors. Regular inspection and maintenance of bonding jumpers are essential to ensure their continued effectiveness. The jumpers should be checked for signs of corrosion, damage, or loose connections. Any necessary repairs should be made promptly to maintain the integrity of the bonding system. Bonding jumpers are a critical component of electrical safety. By providing a low impedance path for fault current to flow back to the source, they help to ensure the rapid operation of overcurrent protective devices, preventing electrical shock and minimizing damage to equipment. Proper installation and maintenance of bonding jumpers are essential for ensuring the safety and reliability of electrical systems. Grounding rods, also known as ground rods or grounding electrodes, are conductive rods or pipes that are driven into the earth to provide a direct connection to ground. They are a critical component of electrical grounding systems, serving to dissipate fault currents and provide a low impedance path for electricity to flow back to the source. This helps to protect people and equipment from electrical shock and damage. Grounding rods are typically made of copper, copper-clad steel, or galvanized steel. Copper is the most commonly used material due to its excellent conductivity and corrosion resistance. Copper-clad steel is a cost-effective alternative that provides good conductivity and corrosion resistance. Galvanized steel is a less expensive option, but it is more susceptible to corrosion. The size and length of grounding rods are determined by the requirements of the National Electrical Code, specifically Section 250.52. The NEC specifies minimum requirements for the diameter and length of grounding rods, as well as the depth to which they must be driven. The depth to which a grounding rod must be driven depends on the soil conditions and the local electrical codes. In general, grounding rods should be driven to a depth of at least 8 feet. Grounding rods must be installed in accordance with the requirements of the NEC. They should be driven vertically into the earth, and they should be spaced at least 6 feet apart. The top of the grounding rod should be flush with or below the surface of the earth. Grounding rods must be connected to the electrical system using a grounding electrode conductor. The grounding electrode conductor must be sized according to the requirements of the NEC, and it must be securely connected to the grounding rod using an approved method such as exothermic welding, listed pressure connectors, or listed clamps. Grounding rods should be inspected regularly to ensure that they are in good condition. The rods should be checked for signs of corrosion, damage, or loose connections. Any necessary repairs should be made promptly to maintain the integrity of the grounding system. Grounding rods are an essential component of electrical safety. By providing a direct connection to ground, they help to protect people and equipment from electrical shock and damage. Proper installation and maintenance of grounding rods are essential for ensuring the safety and reliability of electrical systems. When installing 60 amp service to a pole building, it's crucial to adhere to the National Electrical Code, or NEC, guidelines for grounding to ensure safety and proper functionality. The NEC provides specific requirements for grounding electrode systems, which are designed to protect people and equipment from electrical shock and damage. For a 60 amp service, the NEC typically requires a grounding electrode system consisting of at least one of the following. Firstly, a metal underground water pipe in direct contact with the earth for at least 10 feet. Secondly, a concrete encased electrode, also known as a UFA ground, consisting of at least 20 feet of 1/2 inch or larger reinforcing steel encased in concrete. Thirdly, a ground ring encircling the building or structure, consisting of at least 20 feet of bare copper conductor buried at a depth of at least 2.5 feet. Fourthly, ground rods or ground plates, which are the most common type of grounding electrode used for small services. If using ground rods, the NEC requires that at least 2 ground rods be installed, spaced at least 6 feet apart. The ground rods must be at least 8 feet long and made of copper, copper-clad steel, or galvanized steel. The resistance to ground of the grounding electrode system must be 25 ohms or less. If the resistance is greater than 25 ohms, an additional grounding electrode must be installed. It's important to note that the NEC also requires bonding of all metallic parts of the electrical system, including metal conduits, metal enclosures, and metal equipment housings. This bonding is necessary to ensure that all metallic parts are at the same electrical potential, which minimizes the risk of electrical shock. The grounding electrode conductor, or GEC, is used to connect the grounding electrode system to the electrical service. The size of the GEC is determined by the size of the service entrance conductors, as specified in Table 250.66 of the NEC. The GEC must be made of copper or aluminum, and it must be protected from physical damage. When installing a grounding electrode system, it's important to consider the soil conditions at the site. Soil resistivity can vary greatly depending on the type of soil, the moisture content, and the temperature. In areas with high soil resistivity, it may be necessary to install additional grounding electrodes or to treat the soil to reduce its resistivity. The NEC provides detailed requirements for grounding and bonding, and it's essential to follow these requirements carefully to ensure the safety and proper functioning of the electrical system. It's always a good idea to consult with a qualified electrician or electrical engineer to ensure that the grounding system is installed correctly. The information provided is for general guidance only, and it should not be used as a substitute for professional electrical advice. Soil composition significantly influences the effectiveness of grounding systems. Different soil types exhibit varying levels of resistivity, which directly impacts how well electrical current can dissipate into the earth. Understanding these differences is crucial for designing and implementing reliable grounding solutions. Clay soils, characterized by their fine particle size and high water retention capacity, generally exhibit low resistivity compared to sandy soils. The presence of moisture and conductive minerals in clay facilitates the flow of electrical current, making it an ideal medium for grounding. Sandy soils, on the other hand, are composed of larger particles with less surface area and lower water retention. This results in higher resistivity, hindering the efficient dissipation of electrical current. As a result, grounding systems in sandy soils may require additional measures to achieve the desired level of performance. Loamy soils, a mixture of sand, silt, and clay, offer a balanced composition with moderate resistivity. Their combination of particle sizes and mineral content provides a compromise between the high conductivity of clay and the poor conductivity of sand. However, the specific resistivity of loamy soils can vary depending on the proportions of each component. Rocky soils, characterized by the presence of large rocks and boulders, pose significant challenges for grounding. The limited contact area between the soil and the grounding electrode increases resistance, making it difficult to establish a reliable ground connection. In such cases, specialized grounding techniques may be necessary to overcome the obstacles posed by the rocky terrain. The moisture content of soil plays a critical role in determining its resistivity. Water acts as a conductor, facilitating the flow of electrical current through the soil. As moisture content increases, resistivity decreases, improving the effectiveness of grounding systems. Conversely, dry soils exhibit higher resistivity, hindering the dissipation of electrical current. Seasonal variations in rainfall and temperature can significantly impact soil moisture content, leading to fluctuations in grounding system performance. During dry periods, the effectiveness of grounding systems may be compromised, requiring additional measures to maintain the desired level of protection. The presence of dissolved salts and minerals in soil can significantly affect its resistivity. Salts and minerals act as electrolytes, increasing the conductivity of the soil and lowering its resistivity. Soils with high concentrations of dissolved salts and minerals are generally more conductive than those with low concentrations. Coastal areas and agricultural lands often exhibit higher concentrations of dissolved salts due to the presence of seawater or fertilizers. The temperature of soil can also influence its resistivity, although to a lesser extent than moisture content and composition. As temperature increases, the mobility of ions in the soil increases, leading to a slight decrease in resistivity. However, the effect of temperature on soil resistivity is typically less pronounced than that of moisture content and composition. When designing a grounding system, it's essential to consider the specific soil conditions at the site. Soil testing can provide valuable information about soil composition, moisture content, and resistivity, allowing engineers to tailor the grounding system to the specific needs of the location. In areas with high resistivity soils, additional measures may be necessary to improve grounding performance. These measures may include the use of multiple grounding electrodes, soil treatment to reduce resistivity, or the installation of ground-enhancing compounds. By carefully considering soil conditions and implementing appropriate grounding techniques, it's possible to ensure the safety and reliability of electrical systems in all types of environments.